Okay, I'm Sean Park, and today I'm gonna talk about training deep quantum neural networks, which was published in Nature Communication. So the contents of today's topic is first I will introduce classical neural network and the way we conventionally construct quantum neural network, and the quantum neural architecture of this paper and training algorithm suitable for that architecture. And I'll show some simulation result, which is not very important in this paper. And we will keep on going to the discussions. Okay, first of all, this is a neural network. So we have a model called neurons, which have some input and do a summation and do some nonlinear transformation to produce output. So the network consists of these neurons is a neural network. And well, I guess we are really familiar with this topic, so I'll skip this part. And conventionally, we make a neural network, quantum version of this neural network, like this using a parametric quantum circuits. So we prepare parameterized gates and some entangling gates to construct some parameterized unitary, so we can learn unitary of the our target. But the problems of this architecture is that there is a barren plateaus. It is very vulnerable to barren clusters on which. So what it means is that the gradients or the variation of gradients decays exponentially with the number of qubits we are using. And also, as you can see like this, even if we repeat this layer many times, we cannot really define perceptron. So there is a very little connections between a classical neural network and the quantum version of neural network. So in this paper, the authors proposed a new architecture of this neural network. So instead of training arbitrary unitary that is parameterized by some parameter gates, we are aiming to learn some arbitrary quantum channel. So how to make the quantum channel? So quantum channel in general is just applying some global unitary and tracing out the non-necessary outputs, right? So we input the mixed quantum states from previous layer and perform some arbitrary unitary and to get some output. So this unitary can be our new perceptron. So in this here is the general quantum neural network that this paper are proposing. So these qubits are connected by this perceptron unitary U, which would be like this. So in this input layer should be over here, and the output node should be right over here. So and overall output of the network would be like this. So here we have an input state and some output qubits with output and hidden qubits, which should be initialized into something, and we apply this neural network layer like this, and trace out the hidden and input qubits. Then we should get the output state. So in channel notation, we can make each layer as a channel of that layer, and well, it is just mathematical equation. and we'll keep this notation for simplicity. For some remarks, it seems that since it's a fifth-order network, we can make this unitaries as a control unitary, which has a form of this one. But actually, if we use this form, it makes the channel secure channel which has a zero contact capacity. So the universality will be break. So yeah, you cannot use this kind of control unitary as perceptrons. Okay, so the training algorithm. So in general machine learning, we have input and output. In general, or supervised machine learning, we have just input and output. And what we are going to do is to learn arbitrary unitary V, which transform input to correct output. So naturally, the cost function would be the quantum version of risk function, right? So this should calculate fidelity, and average over that overall training inputs would be our cost. Which is weird if you think about it, because in this case, the higher the cost is, the better the algorithm. So keep in mind that. And after calculating this cost function, we are going to update our QNN or unitary like this. So here K is some arbitrary Hamiltonian, and we will evolve unitary like this. This makes sense, right? So the question is, we are trying to set this K to maximally increase the cost function. So the difference in cost function between this and this unitary would be this. This follows from very tedious mathematical calculation. So we are trying to get this K, which maximize this difference in cost. Okay, so this is the training algorithm that this paper is proposing. Can you see the screen, right? Right. So first step, we initialize some random unitary, obviously, and we propagate or feed for the network and store the output state of each layer. And we are going to update the network using the K matrix of this form, and the M is this one. So this is also from the tedious mathematical calculation that maximize the increase in cost function. Here, gamma is learning rate, and gamma is defined as learning rate. So we can change that. Okay, so the important thing to note is that if you're going to calculate K, we need to know what is M, and M is in this form. And here we see this part is this part. So given some input of input state of layer L-1, we can apply unitary from 1 to J and get the output. That is what this part in this commutator are setting. And the other part is from the auto join channel. So the auto join channel. Let me first explain what is auto join channel. So generally, the channel can be defined like this, and which can be rewritten in the cross operator form, right? So we're taking auto join of this form, right? And which is same as this one. So that's the auto join channel. So if we multiply these two and take trace, it should be Yeah, it should be 용역. Yeah, I'm a little bit confused about the definition, but it should be 0, I think. So that's the yeah. Oh no, sorry. Sorry about that. If we apply this the channel and it's adjoint and take trace, it should be same as the expectation value. So that this is like viewing a channel in Heisenberg picture. Oh, sorry about the confusion. Anyway, so what we need is the state of our previous layer output and the state of the auto previous forward layer auto join channel. Right? So if so, getting this the state inside the commutator is relatively easy. Okay, using this structure, we can simulate or calculate the structure, but the problem is simulating this commutator, right? That's also from supplementary. So from this paper, there's a trick like this. So if you apply this trick, you can actually get the commutator, calculate the commutator. So yeah, that's how we're actually implementing this algorithm in quantum machine. But if you're just considering a classical simulation, we don't need to really consider it, right? But anyway, now the K is clearly defined. We can update the unitary as follows. And we can repeat this step in given specific learning rate and evolution rate, and the cost function would converge. Okay, so this is the simulation of this learning test. So the cost function, the theoretical limit of the cost function is given like this. I guess from the statistical learning theory, I guess, and the here it shows the comparison between the theoretical limit and the simulated cost function, optimized cost function, which really agrees well among all the number of training parameters. So it shows that it's well trained, right? And also the paper did some experiment on noisy training inputs, which means some inputs be replaced by random inputs. Okay? So the number of noisy input pairs increases. Of course, the cost function drops, but the rate is very slow. So there, so our QNX structure will be robust on input training noise. Okay, so discussion. The paper claims that their QNN architecture has no Barron plateau. So they explain the reason as follows. So in the original paper that first argues about Barron plateau states the gradient of a classical deep neural network can vanish exponentially in the number of layers, while the quantum circuit, the gradient may vanish exponentially in the number of qubits. So in the conventional or QNN network, the gradient vanishes as the number of qubits. But in this case, since this is like a classical deep neural network, the gradient decreases exponentially in the depth instead of the width. Okay. And also they use the different cost functions from this paper. So they explained that's why they couldn't observe any barren plateaus in their numerical estimation. Also, they showed some evidence for robustness on not the training, not only the training pair noise, but the depolarizing noise in the unitaries. So the inset figures shows their result, and as you can see, it is very robust. Also, they claim that in this structure they have reduced the number of coherence qubits, but I'm not really agree with this statement, because in this algorithm, if we want to apply this update rule in this network, and if you're only considering quantum parts, not the classical simulation, we need to store the output of this output states of this layer very long time, right? So that means we could reduce the number of coherence qubits because we are tracing out, but the quality of coherence qubits should be much better than the original. Okay, that's my personal thoughts on that, and thank you for your attention. And any questions?
Thank you for presentation. This slide of box one training algorithm. That's the slide. Left one is not fully connected, but right one is fully connected. So
in where? Here?
yes, it's not fully connected, but right one is fully connected between layers. So I didn't understand the difference between them. So can you explain about it?
I guess it's a design choice. Like you can apply the fully connected layers, but if you know that some qubits are not related to, should not be related to other qubits, then the fully connected layers wouldn't be needed. Okay, so yeah, it's a I guess it's a design choice.
The single companies can be getting also of the was your network is the same some states that applied by other linkers are the different linkers. So just get this contribute.
Can you say it again?
그러니까 저 안에 있는 이런 모드들이
네.
어떤 거에 연결되는지.
여기 일단 이 페이퍼에서는 큐빗으로 생각했고요. 굳이 큐빗일 필요는 없지만, 그러니까 큐빗에 묶음 큐빗일 수도 있는데 큐빗으로 일단 생각을 했고요. 유니테리는 이 큐빗, 이 인풋과 아웃풋의 큐빗 간에 있는 유니테리겠죠. 그러니까 이렇게 생긴 거지. 이게 인풋 큐빗이고 아웃풋 큐빗이 되겠죠.
큐빗이라는 건 스타트지점만 큐빗인 거야? 중간중간에 레이어 있는
이게 다 이제 큐빗이 되겠죠.
I have a question about the last one. Yeah, the discussion. I'm not really sure how they can compare the conventional quantum with this version, because it's difficult to talk about, like, let's say, for example, the effective width of the network. In this case, it looks like you need both the number of qubits should be coherent at the same time with the A layer and then the next layer. Right? So you need that many qubits, but then in that case, how do you define the width of the system and how can you compare that?
Okay, so width can be summation of all qubits we are using, but also the maximum number of qubits per layer, right? Because we can reset the qubits.
I mean, not really, no? Because we need 2 layers at the same time. Right?
Yeah. Oh, okay. The summation of the
Right,
yeah.
okay.
Yeah. Anyway, to add remarks in this layer, so if we have many qubits, it operates only on 1 qubit. So in this qubits view, it has only the so this qubit is not related to this qubit. So that is the other reason why it should not suffer from paraplex. But I think you know that it has been proven not, right?
Yeah, actually, it's the PRL paper from May of this year.
Yeah, so they could have been wrong. Okay, so anyway, they simulated in very small scale. So they use 3 to 3 structure here. So 3 inputs, 3 hidden, 3 output qubits. So it would be very hard to observe Baron Pluto in this.
I saw some QNN architecture which uses nonlinear algorithm for implementing activation function, but I think it doesn't use it, right?
Actually, it does because this trace procedure is nonlinear. Right. Yeah, so I think you mentioned very important remark. So that is why this is so analogous to classical neural network. So in conventional network structure, the nonlinearity does not come from unitary, but the function we are applying to unitary, right? So if we just put a general unitary here and parameterize every element, it should be all linear. But in this case, since we have trace, we can do that and still get the complex approximation. Essentially.
Then is it easy to implementing trace operation?
Yeah, you can just ignore the tracing out qubits. Okay, any more questions from maybe Zoom? Oh. Okay, then thank you for listening and thank you for participation for tonight. And see you next week.